Are you ready, kids? Today we're going to be talking about calculus and how it's actually pretty relevant to neuroscientists. The outline for the lecture today is going to be, we're going to go over differentiation, then integration, then multivariate stuff, and then a little bit about optimization using gradient descent at the end. Okay, so the derivative is actually intuitively just the instantaneous slope of a function, or the instantaneous rate of change of a function. So here with this line f of x equals 4x minus 12, the slope of f of x is 4. And f of x has a constant rate of change for the entire line. This is actually pretty easy to tell even if you don't have the equation for f of x. If you use just numerically, you can just calculate the change in y over the change in x for several different points. And you can confirm that it's actually the same. So f of 4 equals 4 and f of 3 equals 0. So if you take the change in y, 4 minus 0, over the change in x, 4 minus 3, you get the slope of 4. And you can confirm that it's actually the same for every interval you take along this line. When you don't have a constant rate of change, such as here, when f of x equals 2 to the x, the derivative is going to be different throughout the function. And so, here the rate of change at x equals 2 is 2.77, but as you increase x, the rate of change will increase as well. So, if you try to numerically estimate the derivative using 2 points as before, you won't get a very accurate estimate of the derivative. But if you remember back from when you first learned about derivatives, the explicit formal definition of the derivative is the limit of the change of y over the change of x as the change of x goes to 0, as illustrated here. But this definition is only useful for deriving the differentiation rules you typically just look up, so we're going to completely ignore limits and how to work with them and go straight into differentiation. First, the notation of a derivative. The derivative of f of x can be written as d over d of x of f of x or f prime of x. I'm going to be using both of these notations in this lecture. D over d of x is called the differentiation operator. There are also several other notations that sometimes physicists or engineers will use, but I'm not even going to include them because they're wrong. Let's go over a couple examples of derivatives to gain an intuition. The derivative of a constant is 0, which means that for a function f of x equals, for example, 2, there's no change in y because it's constant and the derivative will be 0 throughout. The derivative of f of x equals 1 because for any change in x, there will be an equal change in y. When you change the slope of the line, the derivative will just be the slope of the line. For example, here, c. And in fact, this generalizes such that anytime you take a derivative with a scalar multiple, you can just pull the scalar multiple outside of the differentiation operator. A couple other differentiation rules. You will be expected to be able to use other differentiation rules, and I've included a link here on how to find them. First, differentiation distributes over addition. This means that the derivative of f of x plus g of x equals f prime of x plus g prime of x. This does not mean, however, that differentiation distributes over multiplication of functions. In fact, differentiation over multiplication takes this form. The derivative of f of x times g of x equals f prime of x times g of x plus g prime of x times f of x. Lastly, the famous chain rule. The derivative of f of g of x equals the f prime of g of x times g of x. Alright, on to anti-differentiation, otherwise known as integration. Anti-differentiation is literally just the inverse of differentiation. Differentiation takes a function f of x and outputs g of x. Anti-differentiation takes that g of x and outputs f of x. And so, formally, if we write the derivative of capital F of x equals lowercase f of x, then the integral of lowercase f of x equals capital F of x plus c. And capital F is the antiderivative of lowercase f. And this integral form is called the indefinite integral, and it's just trying to find the antiderivative of the function. You guys may remember the definite form of the integral, which is written here, and by the fundamental theorem of calculus, it's just the antiderivative evaluated at the limits. If you'll recall, the definite integral also has a geometric interpretation that is the area under the curve. And you may also remember that the integral has a formal definition that's related to the limit of a Riemann sum as the widths go smaller and smaller. Once again, we're going to sweep all that under the rug because it doesn't really matter. Let's quickly take a break from calculus to go back to a concept we've tossed around for a while, likelihood. In English, likelihood just means probability, but in statistics, likelihood is the probability of observing the data you've gathered given a set of parameters for a model. One thing that people are often interested in are the set of parameters that maximize the likelihood. For example, here, if lambda is our model parameter and the likelihood is on the y-axis, the lambda value which maximizes the likelihood is lambda equals 2. If we're only interested in the maximum value of the likelihood, then we're allowed to apply a monotonic transform to the likelihood. Monotonic means that it is increasing. That is only increasing, like the cumulative distribution functions from before, or that the transform doesn't change order, only spacing. This just means that the maximum of the likelihood is also the maximum of the log likelihood. And while any monotonic function would work, such as square root, the most useful transformation is going to be log likelihood, and we'll show why some of those reasons are in the problem set. So how do we actually find the maximum of the likelihood or the log likelihood? Well, it's actually pretty easy to do by eye, as we saw before. However, what that actually entails is evaluating the likelihood at regular steps and then just picking the highest point or the best point found. The problem with that is that as you have non-zero step size, the real maxima is actually going to be somewhere in between it. And in order to have the distance between the best point found and the real maxima, you have to double your computation time because you have to do twice as many steps. A better way to do it is to use the derivative and start at a starting point and calculate the derivative at that point. Then take a step in the direction going downwards or upwards, depending on whether you're trying to maximize or minimize, but take a step downwards based on how large the derivative is at that point. And so what you'll notice is the derivative of a function is going to be 0 at the final value, or the maximum, or the minimum. And so as you, for each iteration you do, you have your point, you find the derivative, you take a step in the direction that the derivative says to go based on the magnitude of the derivative. And so when the derivative is very steep, you take a larger step, and when the derivative is very shallow, then you take smaller steps, and you're trying to go to the point where the derivative is 0, or the final value is going to be the min or the maximum of your function. Alright, let's get back from our tangents for a one-slide overview of multivariate calculus before we dive into some examples to tie these concepts together. If we have a function that depends on two variables, x and y, we can plot f of x comma y as a surface in 3D space, such as here in purple. It doesn't make sense for us to take a derivative of a 3D surface. However, if we're only interested in how the function changes as we vary x, we can hold y constant at y equals b. When we do this, we have the 2D curve shown here in green, f of x comma b. Since this is just a 2D curve, we can take the standard derivative we're used to by treating y as a constant. When we do this, we get a partial derivative of f with respect to x These curly D's just mean partial. It means that there are other variables which contribute to the changing of this function. We can also do this, do it in the same manner with y. And when we do this, we get the partial derivative of f with respect to y. When we put both of these together in a vector, we get the gradient of f. The gradient is just the partial derivative with respect to each of the basis dimensions. These are the notations that are often used to denote partial derivatives or the gradient. So this upside down triangle here is the symbol for the gradient, and it just means that we have a vector of the partial derivative of f with respect to x over the partial derivative of f with respect to y. Back when I was talking about using the derivative to find the minimum, I was really just describing gradient descent, but it's not really a gradient in one dimension. Gradient descent makes much more sense in a multidimensional space. For example, here. Each number, for example 0 to 1, represents an iteration of the gradient descent algorithm. You can see that each step moves it closer to the minimum, but this is a particularly pathological example, where you end up going back and forth for thousands of iterations before eventually getting to the minimum. Gradient descent optimization is a whole field of study, and there are lots of special ways to add momentum terms and other methods to speed up the convergence of optimization. Therefore, we aren't going to implement our own gradient descent, however, we will see how much faster the optimization works when we give it the gradient. Aw, hells yeah! Finally time to build some models, bust out the pen and paper, and differentiate stuff. Alright, let's say we're up all night to get some data, moving dots all up in my face. We're doing some basic motion coherence psychophysical experiment. All the dots moving to the left, they're obviously moving left. All the dots moving to the right, they're obviously moving right. Some moving left, some moving right. Now we got ourselves some ambiguity. Let's say we got someone to do a bunch of trials with different levels of motion coherence. We want to estimate the maximum likelihood parameters for their psychometric. Alright, what I mean by a psychometric curve is the probability of them responding right given the coherence. And so if the y-axis here is probability of responding right given the coherence, and the coherence is 0, 1, -1, or something like that, the probability of responding right is going to be some sigmoid-shaped curve that goes like this, where when all the dots are moving to the right, the probability of that they respond right is very close to 1, and when all the dots are moving to the left, probability that they respond left is very close to 1, but the probability that they respond right is close to 0. Alright, and now let's assume that the equation for this logistic, or this sigmoid, is just a simple logistic. So this would be y of x, and it's going to depend on two variables, b and m. And so y of x equals 1 over 1 plus e to the negative b times x minus m. So this is just a simple logistic curve. It's pretty basic. And so we're going to try and find the maximum likelihood parameters, b and m, such that this curve is best described by our data. So let's say we have a bunch of left responses and a bunch of right responses and their corresponding x values, or their coherence values. X is going to be the coherence. So let's write in an expression for the likelihood for this model. So for the left responses, so this is just going to be the probability of each of probability of observing each of the data points individually, all multiplied together. So First, let's cover. So I'm going to say L for likelihood equals for the probability of I for I is element of left responses. Actually, I've been saying right before, so let's continue on with right. Probability that I is going to be just y of xi, oops, I, right? So for every point that the person responds right, it's just going to be the product of this curve, product of the y value of this curve. But then we have to include the left responses, so it's going to be also times the product of j element of left for j of 1 minus y of xj. All right, and so this is just the inverse probability, the probability of left given the model with the given parameters. So we want to maximize over our b and m. So if we substitute these in, we're going to get, actually before we substitute it in, remember how we were saying before that we can take, if we only care about finding the maximum, we can instead of using the likelihood, we can use the log likelihood. So instead, let's start using the log likelihood. LL equals natural log of the product of I element. And if you recall your log rules, log of A times B equals ln of A plus ln of B. And so that's one of the really powerful things about this using log likelihood is we can turn these products into sums. So when we do that, when we use this rule, we can split this up into the sum over I
of plus the sum of j.
So now we plug our equation for y into here so that we can actually get it as a function of our parameters b and m. And we get so if we look at this right-hand part of the equation here, if we turn this into a fraction of 1 over 1 plus that, then we get 1 plus e minus, so this can be written as, oops, I'm just going to start putting the variable there. E to the negative b times x minus m over 1 plus e to the negative b x minus m. And then we can actually just multiply the top and bottom here by e to the b times x minus m. and we end up getting
Copy down this.
and then pretty much using the same rule as here, we note that this is equal to sum over I of negative ln of 1 plus e to the negative b x I minus m plus the sum of negative ln of 1 plus e to the negative bx minus m. So that's the expression for our log likelihood. And now, in order to plug this into our gradient descent optimizer in MATLAB, we're going to have to calculate the derivative of this with respect to both b and m. All right, new page. You may have noticed a accidental extra negative sign here. I accidentally put that in when I was copying things over. It's not supposed to be there. But this is the log likelihood function that we're going to try and optimize. So we want to find the partial derivative with respect to x, or with respect to b of this function. So first let's just calculate the partial derivative with respect to b of this part. So we want partial db of negative ln of 1 plus e to the negative b times xi minus m. And so when we do this, negative sign just pops out. So the natural log of, or the derivative of natural log, since this internal part depends on b, is just going to be equal to one over 1 plus e to the negative b times xi minus m times, and this is the chain rule here, d db of ln, or nope, of 1 plus e to the negative b times xi minus m. Right, and this is the chain rule. The derivative of ln is just 1 over x, or whatever is inside. And then the chain rule is the derivative of the inside is to be multiplied here. So then we distribute this this partial derivative to the 1 and the e to that, and we find, remember, the derivative of a constant is 0, so this doesn't matter at all. And so we get negative 1 over 1 plus e to the negative b times xi minus m times, and the derivative of an exponential with our derivative rules is just itself times to the negative b xi minus times the derivative with respect to b of the top, which is just negative xi. Negative xi. And just as we did on the other side, this goes up to the top, and we then multiply top and bottom by e to the b times xi minus m, and we get and when we combine everything, we get negative, negative. 1 over e, xi over e to the b times xi minus m plus 1. So that's going to be the derivative of this part in here. This is the derivative of this part. So it's going to be a sum over this. So let's do the same thing for this part over here. So partial, that was a crappy partial. Partial dB of negative ln 1 plus e to the b times xj minus m. This comes out again, and it's the same, pretty much the same deal as we were doing before. Negative 1. Times the derivative of this top thing with respect to b, which is just, oops, I made a mistake over there. But actually, so we're taking it with respect to b, so this goes out, and it's actually times xj minus m. And we got to do the same thing back over there, too. So when you do this, and now we're dividing the top and bottom by this, so it's actually m minus xj over e to the negative b xj minus m plus 1. And so, oops, yeah, this is right here. We need to go back and change this. So we're taking with the derivative with respect to b, so it's actually negative xi minus m. So it's xi minus m for this. So if we do d dB of the log likelihood equals the sum over I of xi minus m over e to the, oops, apparently I have a button for eraser and I didn't even know. E to the, so that's the derivative with respect to b. I'll do the derivative with respect to m real quick, and then I will give you guys code for the implementation of this in MATLAB for the problem set. All right, now we're going to do the same thing with respect to m. So you'll notice how in the last example we just held m and treated it like a constant and it wasn't a variable at all. Now we're going to do the opposite and hold b as a constant and just take the derivative with respect to m. So once again, just dealing with the inside part of the summation first. Oops. Alright, so we want the partial derivative with respect to m this time of negative ln of 1 plus e to the negative b xi. And we're doing pretty much the same thing. Alright, so negative comes out. The derivative of the natural log again. So it's negative 1 over 1 plus e to the negative b times xi minus m times the derivative by chain rule of this inside part. So partial dm of and then once again, this is a constant, doesn't matter. And we do the derivative of an exponent again, and it is negative. Times the derivative with respect to m of this. So this is where I actually made the mistake last time, is that now the negative b times xi is just a constant and doesn't leave a derivative, but the negative b times negative m is actually going to leave the derivative, which is just negative b, because negative b is a constant here. And so, same multiply top and bottom, blah, 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 plus, plus, we get b over e to the b times xi minus m plus 1. Alright, to the other side real quick. Natural with respect to, what are we doing? M.
Something.
Times the derivative of the inside, which is just doesn't matter again, and so derivative exponent just leaves us with 1. Times by the chain rule once again, the derivative with respect to m of b times xj minus m, which is just negative b. So when we combine these, we get so when we sum these together, alright, so now we have our two equations. We implement these in MATLAB, and I've given you the code for that in the problem set, and then we'll be able to fit this model. In fact, we're going to use a better we're going to fit a better psychometric curve. I'll give you the equation for a more general logistic curve, and you're going to take the partial derivatives for that and fit an even better curve. Alright, sorry for the late upload for this guys. Lots of annoyances in recording this. Hopefully everyone got to see this before the lecture, and we're going to do some cool stuff during the problem set, so get ready for that. Here are some resources, a nice little calculus explain where I got a lot of the images. There's the Coursera calculus course, Wolfram Alpha is pretty useful for checking your work, and then the Wikipedia for calculus